Okay, so we're going to do this Leetcode question, but we're going to do Quicksort. So we're trying to quicksort an array. How do we do that? So Quicksort is a quick way of sorting an array. Okay, so let's see how it works though. Let's take one of these as an example. What Quicksort does is it first chooses a pivot, a random pivot, usually somewhere in the middle. So let's just choose 3, for example. And then it will try and look at all the other elements, and if that element is greater than a pivot, then it puts it on the right hand side of the pivot. If it's less than the pivot, then put it on the left. Now that's easy to do if you have another array. So we just for all elements less than 3, just put we see there's a 1 and a 2 less than 3. Then we can add the 3 in and add the rest, right? But how do we do it without any extra space? How do we do it in place, that is? Well, a neat way is to just swap the pivot with the first element, so we have it at the beginning. It's easier to work with that way. And then we have 2 pointers. We start J here, and I is always kind of tracking the pivot. Then we could do a swap then we could check J. If J is less than 3, then we must swap them. So it is in this case, so we swap them and we get 2 and 3. Alright, so we've swapped them, and then once we've swapped them, we increased I. And that's it for that iteration, and then we increment J. So this is the second iteration, and we check, is 5 less than 3? No. Okay, that's the end of that iteration. We continue. So J continues on, and we see, is 1 less than the pivot? Yes, it is. So we swap I and J, so we get 1 and 3 here. Now we want to make sure that this 5 here, this 3 is less than this 5, because right now things are kind of messed up. We've kind of went past 5. We've already confirmed that it's greater than the pivot, but now we've kind of messed things up. So we need to fix it by incrementing I and then swapping I and J. Right, so this has 2 effects that are neat. The first is I still tracking the pivot, and the fact that we haven't messed things up for elements that J has already passed. Okay, let's try another example. Let's try this. So what's the pivot? We can just choose one in the middle. So there's 6 elements, and so 6 divided by 3. Let's choose 2. Yeah, let's choose 2. So we swap 2 in the first one. Then we start the two pointers like this. We see, okay, is 1 less than 2? Yes, it is. So we swap them. 2, and we increment I and swap I and J again after incrementing I. That does nothing. And next iteration, J increments. Then same deal, we swap them because 1 is less than 2. Increment I and swap I and J again, but that does nothing. Then we increment J because this is the next iteration, and then check if 5 is less than 2. No, it's not. So next iteration is 0 less than 2. Yes, it is. So we swap 0 and 2 and increment I, and then swap I and J again to not mess things up. Okay, and then we increment J because it's the next iteration, and Check if 0 less than 2. Yes, it is. Swap these two. Increment I and swap I and j. So we get 2 and 5. And then j increments because it's next iteration, but that's the end of the array, so we break out of the loop. And now we see that because we have all elements here, which is less than the pivot, and all elements here, which is greater than the pivot. All elements here on the right, all elements greater than the pivot on the right, and all elements less than the pivot on the left. Okay, let's just try do this. But okay, but you see that the array isn't sorted, and we're trying to sort the array. So how does this help? What we can do is we can recursively call that whatever function we just implemented on some subarrays. So if the first subarray is the whole array, then we could call it on something that looks like this. So, so for this entire array here, and then we found that the pivot was 2, so we could call it on this subarray here to sort this space in a pivot, and then sort this space in a pivot. If the length of the subarray is well 1, then we don't. It's already sorted, so break out of the loop. This could be the base case. But first, let's focus on just choosing one pivot and then partitioning the array first. See how we can do that. We can write a void function because we're doing it in place. Call it Quicksort, and takes in a reference to a nums. Right, and we want to choose a pivot. So where we before choose a pivot in the middle, we can choose a pivot in the middle again. So that would be well, we could say nums.size divided by 2. Then what we can do is we swap the nums first element with the middle, because that was what we were doing. We want the pivot to be at the start. That makes things easier. And then for j starting at 1, because if our pivot is here, then we could just start j at 1, because we don't need to swap I and j if they're equal to each other. So if all j is less than nums.size j plus j, then we want to check if we also need to keep track of I, and I should always be keeping track of the pivot element. So if if the pivot is greater than the j, then that means they're not sorted. So we want to sort them by doing what we said before. We first swap both I and j. And once we swap them together, we want to make sure we increment I, so we could do I++. But this is the same as doing a post increment of I here, which doesn't affect what we did before. It just means that after this operation is done, we'll find that I is one more than what it was before, without having this function use the incremented version. Uses the old version and then increments it. And then once we do that, we swap I and j again, like we discussed. Once that's done, let's just leave it as that and return nums after we quick sorted that. So we tried this example. Let's see if we get this. If we quick sorted this. Oh, no, not that. This. should look like this, hopefully. Yep, we get 110025. Right, so that's how we do it, just one partition. But if we want to do it on subarrays, we need some kind of bounds. So like int L, int R, and initially we would call it like 0 and nums.size. Now the very last number has the index n minus 1, so nums.size minus 1. So R is actually one more than an index one more than the end of the array. That's okay, we can use that. And so the mid, what would the mid be? The mid would be L plus the length of the distance between L and R. That would be R minus L divided by 2. So that's the mid. And we want to swap. That can stay the same. Now I starts at L and J starts at L plus 1. And we go all the way up to, but not including R, because R is 1 beyond the end. This remains the same. And that should also work. So let's give that a go. Yep, that works. Alright. Now, let's call it recursively for the subarrays. So you want to do two quicksorts, one for the left subarray and one for the right subarray. You both pass in nums. Okay, for the left subarray, that would start at L and go up to, but not including, what our current pivot is. So we've been keeping track of our current pivot using the I index. It's not mid because the mid index would have changed. In fact, that might be a bit confusing, so let's put R minus L here. That's the mid, and we want to go up to I, but not including I. Here we want to go up to I plus 1, including I plus 1, all the way up to R. Alright, so let's give that a run. We forgot the base case. So at some point you will have L and R, a distance of 1 next to each other. In that case, we would get an infinite loop and this would never end. So actually, let's see what's happening. Let's see out the L and R and run that again. Okay, so we get 0, 0, whole 0, 0, 0, and 0, 0. Alright, so we've never handled that case. What we can do is say if R minus L is less than or equal to 1, then just return. And hopefully that handles that case. Okay, awesome. Now it's actually sorted. Let's give it a go with one of these. Awesome. Let's give that a run. Hopefully that works. Looks like we made a mistake. What would you... we want to swap nums L and R, okay. That's one bug. Oh, yeah, that works. Great. Now there's one other thing that we could do. Let's consider the case where our array is just a whole bunch of identical elements. What happens is when we choose a pivot, it's going to be 2. So if we try to sort so that all numbers, so that if nums I is greater than nums j, so if the pivot is greater than any of these numbers, then we want to put that element to the left of the pivot. But in this case, we won't put any of these to the left of the pivot because they're all equal to it, not less than. So I would be here, j would be here, and what would happen would be, we would go through this entire array without sorting anything. I would stay at the start, and then we try and do the recursion on a subarray. Would pass in L and I, so that will be just pass in 0, 0 here. Here it would pass in I plus 1 and j, and that's not trivial because that's like almost the whole array minus 1. It's the whole array minus 1, and that would repeat. And so we would start at j here, loop through all of those, and then we do a subarray on this, and j would start here and repeat. Right, so that's n squared. That's not good. So a way we could deal with duplicate arrays better is if we keep a flag. If we start I here, start j here. First we ask, is this element equal to the pivot? If it is, then I want to put it to the left. And I want to set the flag to, I want to flip a flag so that the next time I encounter an element equal to the pivot, I don't put it on the left, and then I flip the flag again. So then this way, eventually I'll have half the 2's to the left of the pivot and half the 2's to the right of the pivot. Okay, I'll show you what you mean. What I mean, so let's have a boolean called let's just call flip is equal to false, and every time nums I is equal to if nums I, so if the pivot is equal to nums j, then I want to flip. I want flip to be equal to its inverse. And here I can say if nums I is greater than nums j, or in the case where they're equal, so if nums I is equal to nums j, in the case where they're equal and flip, then I want to put it to the left. Otherwise, next time I meet the same number equal to the pivot, I don't put it to the left. So then this way I get roughly half of the 2's on the left of the pivot and half the 2's on the right. And we can confirm this. So let's not do the recursion and just see out the length of the left half of the array and see out the length of the right half of the array. Minus 1. And in the case here, we can say 2, 2, 2, 2, 2, 2, 2, 2. Right, we get 4, 4, perfect split. Now, let's see what happens if we don't do that. So let's delete all of this code and comment this out. What would be the partition be like? 0, 8, not a good partition at all. So this is definitely a good thing to do. Let's give that a run. Let's try it on a normal example. Oh, and I need to uncomment this. Also works. I've tested it and it doesn't really actually improve the time. In fact, it kind of got worse, but I'm assuming that's because they haven't really tested it in the test cases that they provide. But that's Quicksort. Now, it could also be the case where they give an example where the middle elements are in the middle, and it could state in a rare case it will still take n squared time. If we want to make it really random, we could still do that by calling rand function. And rand function turns a number between 0 and a very large number as an integer. So we could get that number, take a modulus of that and r minus l. R minus l is the length of the array, length of the subarray. So imagine if rand, so the maximum, so this ranges between 0 and the length of the subarray minus 1 plus L. So that would do what we want. Okay, so that's probably a better Quicksort. Okay, we get 88. Got good memory usage though, because it's in place. But yeah, that's about it for Quicksort.